work to 4.5, here is questions 1 through 3. Okay. Here's 4. Okay, and then 5. So I did 5 a little differently just to kind of comes back in chapter like 7. So just because I want to make sure we're getting through all of our content, we're going to postpone looking at what this is called right here, which is a differential. So dx is what we call a differential. So a differential is basically the same as saying the difference between them. So the differential is what's the difference between 17.99 and 18. So that represents dx. That should make sense. Differential or derivatives are the change in x. So if the original is 18 and the new point 17.99, what's the difference or the change between them? It's 0.01. So a differential or dx simply represents the change between them. Okay, and then 11 through 14. Okay. Any questions at all on the 4.5 linearization homework? Hopefully, again, that was kind of like the summary of linearization for you. Hopefully it all sort of makes sense. Like I said, I know there's a couple more pages in the notes. Those notes are on what we call differentials, which is kind of what I show you in example 5 here. The only thing that is different on those parts of the notes to what is in this what we've been doing is using that narrative or that piece of information called dx, which hopefully by now you know stands for the change in x, or represents the change from 17.99 to 18. Video on AP Classroom to try to give you an idea of what related rates were, so that I didn't have to, again, feel like we were kind of walking into today without that understanding. So let me give participant and host back to myself on the computer, because for whatever reason the computer didn't want to open my OneDrive, so we switched to hosting on the iPad. But now we're going to give the host back to the computer and share with you our new notes. So as we work through the notes, I did actually cut out some sections because AP went over some major changes in the past few years. So in 2019, they changed the AP exam. Well, obviously, there wasn't a 2020 spring exam to happen that was a true exam. So you guys are the first group that are actually going to take the new true AP 2019 changes. And with those changes came some of the related rate expectations. So that's why I sent you to AP Classroom for that video. Differentiation. So related rates are going directly to take me back to implicit differentiation. We are going to be looking at rewriting equations using Leibniz form, which means we're going to have dy, but now it's going to be dy dt, because for related rates, they're actually talking about a rate. If you think about a rate, it usually relates to change in time. So related rates are going to be our change with respect to change in time. So for some of you, I actually saw when I was passing these out, you were looking at this. Calculus can be thought of the mathematics of change. That is truly the definition of calc. Calc is the mathematics of change. So words that mean change are increasing, decreasing, delta, shrinking, growing. Those all mean change. You have change in time. So like I said, related rates are all going to be with respect to dt, where dt is change in time. So all related rates are going to be involving a dt, where dt has to do with the change in time. So when we talk about quantities for related rates, we're going to talk about them in terms of d dt. When we talk about derivatives of related rates, we're going to use d dt. So all derivatives are going to be with respect to time. So all derivatives are going to be with respect to time. And that's why I said going over that dx from the previous set of notes wasn't necessarily important, because we're going to talk so much about linearization and change in time and change with related rates that you're going to be okay. All right. So related rates. Our goal is to solve related rate problems. So we have those few examples on that next slide. So for related rates, we're going to differentiate everything with respect to time. So you can see I took the derivative with respect to t. You guys are so often thought and used to taking the derivative with respect to x that this is adding a new part to it. So when you take the derivative of z cubed with respect to t time, it's still the derivative of z, but now it's the derivative of z with respect to t. So you have to multiply by dz dt. Kind of like when you took the derivative of y, you had dy dx. Now when you take the derivative of variables, they're all going to be with respect to t. So instead of being dy dx, it's going to be dy dt or dz dt. Or in the case of a trig function with theta as our angle, it'll be d theta dt. Because it represents the change in theta with respect to the change in time. A related rate is the change in theta with respect to the change in time. And what's happening as we work into related rates is that we are going to change from just having a single variable to multiple variables. So there are some strategies. They're very similar to the optimization strategies. So I'm just going to give you a second to read through the strategies 1 through 7 for solving a related rate. So I'm going to give you about 30 seconds to a minute to just read through that. Okay. So, hopefully as you were reading through this, you recognized and picked up on some of the key ideas that are duplicated from optimization. When we optimize problems, the very first thing I told you to do was to draw a picture. Then I asked you to label the picture and write down your equations. So 1, 2, and 4 are very, very, very similar, as well as being able to create a single equation. And just like the last time, once you get your answer, you have to plug that answer back in to find the other answers. The only thing that's really different, and we did it a little bit in optimization, for related rates, they really like to make you write and justify what you're saying, telling, or doing. So a lot of things that we do with related rates, you're going to be expected to put into words. So like I said, we skipped over because I kind of had you look at these with the notes. So this isn't in your packet. I'm just going to walk through real quick our basic formulas and what they would look like now. If this is something you think you want or need, you're more than welcome to write it down. It's also in the video, so you could go back and copy it from there. But we're not going to go through and actually do these problems because they were a lot of what you saw yesterday. Perimeter is typically thought of as 2L plus 2W. In a related rate, change in perimeter is dp dt plus 2 dl dt plus 2 dw dt. Area, this is a product. So that means you have to do first times derivative of the second with respect to time plus the second times derivative of the first with respect to time. So the derivative of area gets a little bit messier. Area of a triangle. So again, we talked about how we're using a lot of geometry now. You will not believe how often in a related rate we use Pythagorean Theorem. Pythagorean Theorem is going to be used a ton in this unit. So derivative of Pythagorean Theorem can be done two ways. You can do it with c squared equals a squared plus b squared. When you do it this way, what's nice is all of these 2's cancel. So it comes c dc dt equals a dA dt plus b dB dt. So what's nice about doing it with the squareds is all the 2's cancel. for the hypotenuse this way. Once again, and this way you have to divide by your c to isolate. We don't really isolate as much in related rates as we have in past algebraic problems. Okay, volume of a cylinder and surface area of a cylinder. So once again, we're going to be using our volume and surface area formulas a lot and taking their derivatives a lot. Now, cylinders become a bit of a pain because what do you know about a cylinder? We now have R and H being multiplied together. So that's two different variables. So two different variables creates a product rule, and it's going to force us into a situation where we have to substitute to get rid of maybe one of the rates. Okay, so we're going to pick up today with example 3. So we're picking up today with example 3. This is one of those common calc problems that you don't go through calc without doing. A ladder. So a 10-foot ladder rests along a vertical wall of a building. If the bottom of the ladder slides away from the wall at a rate of 1 foot per second, how fast is the top of the ladder sliding down the wall when the bottom of the ladder is 6 feet away from the wall? So, step 1, draw in a picture. The best way to understand what's happening is to draw what's happening. So here's my ladder pushed up against a wall. If the ladder is 10 feet long, we're going to call that length Z. The ladder is sliding away from the wall or down the wall, so it's going down and away. So what that means is the height the ladder is from the top of the wall to the ground is shrinking. If a height is shrinking, what do we expect that rate to be? Should it be positive or negative if this distance from here to there is going down? If the distance is decreasing, my rate should be negative. Thank you. Okay, so let's label the rest of this. We're told if the bottom of the ladder slides away from the wall at a rate of 1 foot, so we'll call this X and this Y, because that's what they would look like on the XY plane. That means my rates are going to be dx dt, dy dt, and dz dt. We know Z is 10, and we know the bottom of the ladder is 6 feet from the wall, so that's my X. So we don't know Y. 6 blank 10 is a Pythagorean triple. What's my missing Pythagorean triple number? 8, thank you. So this is a 6, 8, 10 triangle. So you don't have to do Pythagorean Theorem to find that missing length. You should know it. That rate of 1 foot represents dx dt. So dx dt is 1. That's the rate it's moving away. We're trying to find how fast the ladder is sliding down. So we're looking for dy dt, which means we're missing one key piece of information, dz dt. What would the rate of change of the ladder be? Yeah, it's 0. Because is the length of the ladder changing? No. So that means the rate of change of the ladder is 0. So I told you we're going to be doing a lot of Pythagorean Theorem. The equation we're evaluating is going to be the Pythagorean Theorem using x, y, z. That means we differentiate it. Guys, I'm so sorry. I don't know why it keeps doing that. Actually, let's be smart. I'm just going to use the iPad. Okay. So that means if you find your derivative, it's 2x dx dt plus 2y dy dt equals 2z dz dt. And like I said before, anytime you have Pythagorean Theorem, those 2's are going to go away. So we found our geometric equation, we derived our geometric equation, and now we're going to substitute into our geometric equation what we know to find what we want to know. So I know x is 6. I know dx dt is 1. Y is 8. I'm searching for dy dt. Z is 10. dz dt is 0. So that part actually zeroes away. So I get 8 dy dt equals negative 6 divided by 8, or dy dt equals negative 3/4. So what that means is the ladder is sliding down the wall at a rate of 3/4 feet per second. Why didn't I write my rate as negative? Because I said sliding down. Excellent. So you just have to be really cautious. If I imply that it's sliding down and the distance is shrinking, my rate has to be positive in my equation. And that's what makes related rates so challenging, is because sometimes you're going to be given the words and you have to put that into a picture, but they're not going to put the negative in the word. You have to be able to imply. So like if it says a balloon is shrinking at a rate, you have to know that that dV/dt value is negative. So they're not always going to give you the negatives in the problem. Okay, example 4. This example is almost the reverse of what we just did. This example is the reverse of what we just did. So now instead of the ladder sliding down, the ladder's going up. So our picture stays the same, but the variables and their values have changed. Now my ladder length is 15. So I tend to use X, Y, and Z because, except for Z kind of sometimes looking like a 2, they're common variables. I always try to put X along the horizon because that's where it is if this represents the origin in a coordinate plane. And as you get into three-dimensional spaces, or if you're in physics, I believe you use Z for the 3D space because that's the X, Y, Z plane. Z is what's out in that third dimension. So this time my ladder is 15 feet. The ladder is being pushed along the ground toward the building, which means that X is decreasing and Y is increasing this time. So that means if it's pushed along the ground toward the building, the distance away from the building is shrinking at a rate of 3 feet per second. So dx dt is negative. The ladder is 9 feet above the ground, so I'm given y. And anybody know x without doing Pythagorean Theorem? What's 9 divided by 3? What's 15 divided by 3? 5? 4. So that would mean x is, exactly, x is related. It's a 3, 4, 5 triangle. Right. So to get your x value, what do I do with that 4? Perfect. Multiply it by 3. So 9, 12, 15 is a multiple of a 3, 4, 5 triangle. dz dt is once again 0. We're looking for dy dt. If you become confident in your derivative of x squared, y squared, z squared, and you don't want to waste the space with the 2's, I'm okay with that. So if you're comfortable jumping to x dx dt, y dy dt, z dz dt, that's fine. And then we're going to plug in what we know and solve for what we need. So we get dy dt equals 4 feet per second. So what that means is that the sliding of the ladder is now increasing or moving up the wall at 4 feet per second. So the ladder is moving up the wall at a rate of 4 feet per second when the ladder is 9 feet above the ground. Feeling good? Liking ladder problems? What if I change the ladder to have an angle? So, same ladder, same problem. All the information we just found is true. So you're on example 5.
Or is it 4B?
It might be 4B. Yeah, it is example 4B. Sorry. I just looked at your note packet. So the drawing we did in 4A stays. That holds true. So I just obviously kind of erased and kept my drawing. But now we want to know how fast is the ladder's angle changing. Actually, this may not be the letter angle yet, is it? Oh no, at what rate is the angle made? Yes. For some reason I didn't put it on my slide. So it says, at what rate is the ladder changing with respect to the ground? So my theta is going to live right there.
Michael West, please come to the office. Micah West, please come to the office.
So again, everything else stays the same, but now my theta is right there. And I'm looking for the change in theta. So my question mark now is, what is d theta dt? Any thoughts on an equation we would have used in trig pre-calc with a right triangle given side lengths? Give you a hint, he's a chief. What?
I was gonna say we don't. I have no idea what you're talking about. We barely learned trig last year.
What? Chief blank? Like in math, you didn't learn chief SOHCAHTOA? Guys, do you not know who SOHCAHTOA is? You have to know SOHCAHTOA. You should have done SOHCAHTOA.
I mean, we know like the pattern.
Right, so like when I was trying to give you a hint and say, hey, like chief blank, I was trying to get you to tell me SOHCAHTOA. And we did this at the Chief SOHCAHTOA. That's just like how you remember like SOHCAHTOA as like a role. Because SOHCAHTOA sounds like an Indian name, so they always called him Chief SOHCAHTOA. And then you like, your math book has it like in there. Maybe not this book.
We barely got to any trig last year. Like, whatever trig I know, I have
Learned in here. Okay. Okay, so SOHCAHTOA. Sine equals opposite over hypotenuse. Cosine equals adjacent over hypotenuse. For this problem, because we know every rate and every side length, you could actually use any of the trig functions SOHCAHTOA's up there. I tend, since we found dy dt, I'm going to try not to pick the derivative that's going to involve side y. So side y, in the case of SOHCAHTOA, is my opposite, z is my hypotenuse, and x is my adjacent. So I personally am going to pick the trig function that doesn't use opposite, because we found dy dt. And what if we found it wrong? Now you're going to do a whole nother part of the problem with a wrong answer. So since I found dy dt, I'm not using it for my problem. So I'm going to pick cosine. So my function is cosine theta equals adjacent, but in terms of this problem, adjacent is x over hypotenuse, which is z. So the SOHCAHTOA, or right triangle trig, tells me that cosine theta is equal to x over z. Take the derivative. That's the way you're going to get your rate. So the derivative of cosine is negative sine theta d theta dt. Hey, that's what I'm looking for. Equals the quotient of x over z. So that's whole di minus high do all over ho. Plug in what you know. So we have negative sine theta d theta dt equals 15 times negative 3 minus 12, times 0. Well, that's nice. All over 15 squared. Oh, that's kind of nice too. 15 and 15 squared cancel. Only because this zeroes out. If that didn't zero out, then I couldn't cancel my 15s. But because it's 15 times negative 3 minus 0, it just becomes one piece of the problem. Do you remember like when you did like 3 times 3 times 3 over 3 times 3? Like how you can cancel numbers like that? That's what we're doing here. This is kind of like saying 15 times negative 3 over 15 times 15. So those 15s can cancel because they're the same.
Threw me off for a second because
It's all good. All right. Here's the thing, guys. We actually know one more piece of information. We actually know from SOHCAHTOA. Oh, I hit eraser. We actually know from SOHCAHTOA what the sine of theta is. Because sine theta is actually opposite over hypotenuse. So I can replace sine theta. So it becomes negative. So sine is opposite, which is y. Hypotenuse is z. D theta dt equals negative 3 over 15. But they both divide by 3. So negative 3 over 15 becomes negative 1/5. So I can solve for d theta dt by multiplying both sides by my reciprocal. So you get negative 1/5 times negative 15 over 9. So two negatives make a positive. And you get negative or positive 3/9, which becomes 1/3. So what that means is that the angle is increasing at a rate of 1/3, and it's an angle or a theta, so that's radians per second. So that means that the angle is increasing at 1/3 radians per second. If this angle is getting bigger, what do you think about the angle opposite it up here in blue? That would be getting smaller, right? As one angle in a triangle, right triangle is increasing, the other angle would be decreasing. Would the angles be increasing and decreasing at the same rate? Yeah. So if you find the bottom angle down here, and that's that positive 1/3, the angle up here would have to be negative 1/3. And the reason for that is because angles in a triangle are proportionate. One angle can't be getting bigger at a faster rate than the other one's getting smaller, because they have to always sum to 180 degrees. So pause, get a breather, take a break. It's 9:22. Come back at 9:26. I know we missed our first break when the bell rang, so take your 4-minute break now. Stretch, get your blood flowing, move around. There's almost guaranteed to be one on the AP exam. I don't know a year that there hasn't been a rate in and a rate out problem. Where did I put? There's my Apple Pen. All right. So take a minute. I want you to read through. That's why I put like the work on top of the work that's up there. I want you to take a minute, read through, and underline key words, key features, and key ideas from what you think is happening in that problem. So, first things first, draw a picture. Like, what is the shape of this example? It's being poured on a beach, creating a cone. So imagine your cone. The height and radius of a cone form a 90-degree angle. The height of the cone is from the ground to the tippity top. The radius is from the circular base in. In this problem, we are given a piece of information. The radius is always equal to twice the height. So really what that means is, and my cone's kind of taller than it is wide, what that really means is that this cone is wide and short. And your drawing doesn't matter. It doesn't have to reflect that. What it does have to reflect, or what you do need to do, is make sure you come up with the relationship between radius and height. We're given one more thing. We're given that it is poured at a rate of 20 inches cubed. If something is cubed, what is it relating to? Volume. But the word rate's in front of that. So this isn't the volume of the cone. It's the dV/dt of the cone. So it's kind of like 20 over 1. 20 inches cubed every 1 second. What am I looking for? I'm looking for how fast is the height changing. So I'm looking for dH dt given h equals 2 and h equals 6. So it's kind of like 2 problems in 1. So the geometric equation that's going to relate all of this is the dV/dt we have. So if I have dV/dt, I need V so that I can find dV/dt. So what is the volume of a cone? Anybody know? Perfect. Volume of a cone is 1/3 pi r squared h. Typically, if you need a formula, the AP exam gives you that formula. They're going to give you volume, but not dV/dt. Because in the case of this dv dt, we have two variables. But I'm only looking for one rate, and I'm only given one rate. Which is why that relationship at the beginning is so important. I have to get rid of r by substituting r in. So we're going to change volume to be 1/3 pi, but instead of r, we're going to change it to 2h squared times h. Which becomes 4/3 pi h cubed. Derivative of volume becomes 4/3 pi times 3h squared dh dt. So my 3's can cancel. So dv dt is 4 pi h squared dh dt. So now we're going to plug in what we know. So we have two h values, and we have to find two different dh dt's. So 20 equals 4 pi 2 squared dh dt. So you have 20 divided by 2 squared, which is 4. 4 times 4 is 16. So dh dt is equal to 5/4 pi. And then this would be in terms of inches, because dv dt was inches per second. And that should make sense. dh is height. So change in height would be inches. Change in time would be seconds. So dh dt is equal to 5/4 pi when the height is 2. Do we anticipate the dh dt when the height is 6 to be the same or different? Is dh dt when the height is 6 going to be the same or different? What do you think? Okay, so we have one different. Anybody think it's going to be the same? Anybody think they have no idea?
I think it's gonna look the same until you plug in until you plug in the h for 6, which is
Exactly.
36 times 4.
Instead of 4 times 4. Exactly. So it's going to change because you're plugging in a new number here. So the red is kind of like our stall point. So then this is for h equals 2. And then the second part is h equals 6. And it's exactly as suggested. Now 6 squared gives you 36. 36 times 4 is much larger. It's going to be 144. So my dh dt is going to be 20/144 pi inches per second. Okay. We're going to pause there for today then. Tomorrow, well, my example says I'll leave for tomorrow. 1, 2, 3, 4, 5, 6, 7. We'll do one more example and then we'll be done for today. I just don't have too much tomorrow either. Okay, so a car is traveling west at 50 miles per hour and a car is traveling north at 60 miles per hour. Both are headed for the intersection of the two roads. At what rate are the cars approaching each other? When car A is 0.3 miles and car B is 0.4 miles. So here's my roads, here's my intersection. Car A is traveling west. Car A is traveling west, so west is this way. Car B is traveling north, so he's coming in from here. So here's car A, here's car B. So this time both cars are approaching the same point. So if the cars are approaching the same point, do we think their rates of change are going to be positive or negative? Is the distance between them getting bigger or smaller? They're approaching an intersection, so what's happening to the distance between them? It's getting smaller. Something's getting smaller, their rates are going to be negative. So if car A is traveling west and going to the point, that means dA dt is negative 50. Car B is going to that point, its dB dt is negative 60. C is the distance between them. That's what we're looking for. We want to know, how is this distance between them changing as they get closer and closer to the intersection? So A is 0.3 miles, B is 0.4. So what's that make C? 0.5. 3, 4, 5 triangle again. All I had to do is take 3, 4, and 5, divide them by 10. And you get 0.3, 0.4, 0.5. So we have a right triangle approaching an intersection. Therefore, we have Pythagorean Theorem. But now instead of x, y, and z, we used A, B, and C in the context clues of the problem. So that's A, dA dt, plus B, dB dt, equals C dC dt. And this time we're looking for dC dt, and this time that change is not 0. With the latter it was constant. Now all parts are changing. So we have 0.3 times negative 50 and 0.4 times negative 60. This would be a non-calculator question, guys. They would expect you to know that, like, what 0.3 times negative 50 is. If it's hard for you to see it as a decimal, remember that all of those decimals can be converted to fractions. So again, if you're somebody that struggles with decimals, 0.5 is the easiest. But 3.3 is really 3 over 10. And 0.4 is really 4 over 10. What makes changing it to a fraction nicer is now 50 divided by 10. You know really easy. You know 50 divided by 10 is 5. So then you get negative 15. 60 divided by 10 is 6. So you get negative 24. Equals 1/2 dC dt. So the reciprocal of 1/2 is 2. So you're going to multiply both sides by 2. So negative 15 and negative 24 is negative 39. Negative 39 times 2 is negative 78 miles per hour. So again, that should make sense. The distance between the cars is shrinking at a rate of 78 miles per hour. For part B, suppose the cars have traveled through the intersection. Now we're talking about where they are 2 hours later. So B is going to be north of the intersection. A is going to be west of the intersection. Their rates have now changed to positives. You could find their distance knowing their rate. So remember, distance equals rate times time. So if their rate's 50 and they travel for 2 hours, that means it's 100 miles. 60 at 2 hours is 120 miles. Unfortunately, a 10, 12 is not a Pythagorean right triangle triple that we know. So to find C, you had to actually do your Pythagorean theorem. And then it should make sense that their rate of change isn't changing. Their velocity isn't changing. Therefore, the rate of change between them isn't changing. But now they're getting further and further apart at 78 miles per hour instead of closer together. Therefore, that dCdt value is positive. So it didn't matter how far apart they were, since they were traveling at a constant, then their rate of change is also constant, which is why I added this as like part B. Okay, so then I gave you that worksheet. So I believe, where did I put my worksheet? Okay. But I want you to just do problems from there as opposed to our book. Well, let me make sure I gave you the right handout, because I had one that said homework and one that said classwork. Yeah, which is fine. So, because the first one's the ladder, and then it's a tank, which is a cone again. The camera being mounted is a SOHCAHTOA one. And then the only one we didn't really talk about was a sphere. So for number 5, volume of a sphere, if you want to write it down, for number 5, the volume of a sphere in a hot air balloon is equal to 4/3 pi r cubed. So it's going to be just like our cone, but you have to use a different volume. And then 6 is a cone again, and 7's just like our cars. So you guys are just doing those 2 handouts. It's 1 through 8. You have about 15 minutes now. You can read through them if you think you have questions or concerns about any of the formulas. I will gladly help you with that, but you're doing 1 through 8. On that related rates classwork.